Hello, since we can't be face to face, I thought I would create this video that goes over the exam 2 version 1 solutions that for the exam you just took. So I'm going to go through each of the problems. You can speed through them if you have them correct and look for the one that you need to understand. So the first problem looks at using net present value to evaluate the three alternatives listed there. And we're going to use an 8% minimum attractive rate of return, and all the projects have a 15-year life. So let's go ahead and look at the first one. So what I've done here is I've drawn a cash flow diagram with the initial cost of 10 million, the ongoing expenses of $1 million a year, and the income of 3 million a year. The salvage value then is also included at 3 million at the end of the time period. So I'm going to set up a net present value equation to figure out what the net present value of this is. So I'm going to say negative 10 million because that's already at time period 0. I'm going to take the difference between the income and the expenses, multiply it by a P given A, find the present value given this annual values for 15 years. And then I also add in the present value of the 3 million that's occurring in time period 15. So this value, then I just look up the values in our tables, and I get the net present value of 8,064,600. So that we're going to remember that, and then we're going to look at the net present value for the second one. So in the second case, we're going to look at what's the initial cost. What's the present value of this new product line? So there's initial cost of 12 million, ongoing expenses of 500,000 per year, and then income expected to be 4 million per year. And there's no salvage value in this investment. So I can set up the equation where I have minus 12 million occurring at time period 0 already, then the difference between the income and the expense, and I multiply it by P given 8% for 15 time periods. Look up that factor in our table and get a 17,958,000 net present value. Now, the last one I'm going to look at is this assembly line. So what this is saying is we have an initial cost of $7 million, but it will allow us to save money along the way of 700,000 per year. So what that really is saying is that I'm going to have an investment of 7 million. I have no income, but I have lower expenses. So I have a minus 700,000, which is a positive number. And then I'll go ahead and multiply it by that P given A value to get to the minus 1,808,350. So then I'm going to look at all of these net present values and see what I want to do is choose the highest one. So the project that I would recommend is this new product line for almost $18 million net present value. So problem number 2 has two parts in it. The first is to actually calculate the payback. So in order to do that, what I'm going to do is calculate cumulative cash flow. So I start with a negative 6,700. Then the first year I have 1,000. So that means if I add that up to the negative 67,000, it's negative 6,700 is negative 5,700. And then negative 4,600, and then each year, subsequent year, I'm adding all of the positive cash flows together until it becomes positive. So what that tells me is that somewhere between year 5 and 6, I get a positive cash flow, and I need to figure out exactly where that is. So the payback is going to be year 5 plus the $700 I need in order to get to 0 divided by the $1,500 that I'm getting in year 6. And that gives me a payback of 5.47 years or 5.5 years. And that's the answer. Now, the next part of the problem asks me to think about payback and what are the two major problems in it. Now, the first is that it doesn't consider time value of money. So we're just adding these values together. We're not discounting them at all. And the second, there's no way to include cash flows that occur after the payback period. So if there's a huge positive cash flow in the future, way past payback, it doesn't impact positively the cash flow, or even if there's a negative, it won't impact negatively the evaluation of the project. So let's look at problem number 3. A manufacturing plant needs to replace an air compressor, and there's 4, and there should be 3 options there. There's only 3 options. So what's preferred? Now in this problem, since the evaluation technique is not specified, you'll need to decide which to use. Since the lives are unequal, the method that converts everything to A, or annual values, is the best technique. And so I'm going to use EUAC, which is equivalent uniform annual cost. Since all the values are costs, I will look for the lowest cost alternative. So I'm going to go ahead and, for the first problem, it's that I'm going to convert the initial cost into an A value by multiplying by A given P 6% for 6 years, and then add the 1,500, which is an ongoing maintenance cost. And then I look up that factor in the table, and I get a 3543. And then for the second project, I do the same procedures. I take the 20,000, but I'm spreading it over 7 years in this case and adding it to the 500. So then I get 4,082. The next one, I'm going to be taking the initial cost of 15,000 and spreading it over 8 years, and then also adding the A value that's already given of $1,000, and that gets 3,415. And what I'd like to do is look for the lowest cost alternative. So I would say we're going to choose the Jackson HW75. The next project, I'm going to look at what is the internal rate of return on this stock purchase. So what I said is that I bought Nike 10 years ago for $50. And now I'm selling it for $67. So what's the internal rate of return on that? So I set up a net present value problem, and I set it equal to 0, and I solve for I. So because the peak of an F factor is actually 1 over 1 plus I to the n, I'm going to substitute that in there, and then I'm going to directly solve for I. So I in this case is 2.9% per year. The next problem, I want to use IRR incremental analysis to determine which of the following is the best alternative. So the first step in this is I'm going to calculate the rate of return for each of the projects. So I'll first do the number 1 project, where I have $1,000 and then a $1,300 return in 2 years, and I'm going to substitute that equation for the factor notation so that I can directly solve for I. And that means I get I is equal to 14%. Now I'm going to do that for all of the projects, each one of them individually, and I get an internal rate of return for each project. Now I know the hurdle rate is 10%, so anything that's less than 10% I'm going to drop out. So number 2, number 4, number 6, and number 7 are all dropped out. Then the next thing I'm going to look at is that alternative 1 and 5 have the same investment amount, but 1 is a higher return, so I can eliminate 5 also. So now I just have 1, 3, and 8 to compare. So the order of the analysis, I go from lowest investment amount, which is project number 3 of $600, and then project number 8 of $900, and then project number 1 of $1,000. So I'm going to go and take the difference between 8 and 3. So I take the initial investment is $300 and the return is $300 in 2 years in the future. Now that's a 0% return. I'm not getting any return at all, which is less than the hurdle rate of 10%. So that means that the extra $300 does not give a return higher than 10%. So we're rejecting 8. So now I'm going to get rid of project number 8. I should not have gotten rid of project number 3 on this because I'm still comparing that. So project number 1 to 3 is I'm going to take the difference of $400, and then I'm going to return in year 2 of $500, which is an internal rate of return of 11.5%. This is greater than 10%. So since the extra $400 does give a return higher than 10%, I accept 1. So my answer for this problem is I'm going to go with project number 1. Now the last problem in the exam is looking at this benefit cost analysis. So the state of California is considering a bullet train between LA and San Francisco. The initial cost is $80 billion with ongoing maintenance of $1 billion per year. In addition, there'll be a $20 billion overhaul that will occur every 10 years. The ongoing benefits from the paid ridership and increased economic activity will be $9 billion annually. Assume the life is forever, infinite, and a required return is 6%. So is the project justified? So what I'm going to do is I'm going to go through and do the costs. So in this case, I've laid out all of the costs, the initial cost, the $1 billion per year, and the $10 billion every 10 years. And then the benefits are $9 billion per year, continuing forever. So now what I will need to do is calculate the net present value of the costs and the net present value of the benefits. So the net present value of the costs are going to be 80 plus 1 divided by 0.06, because that is the equation where n is equal to infinity. I can calculate the present value is a over I. And then the 20 billion per year, per every 10 years, what I've done there is I've taken that 20 billion and converted it to an annual value, which is going to occur every year for 10 years. Now that 20 billion, since it's recurring every 10 years, that A value I just calculated will be occurring forever. And so I'm going to also divide that by 0.06. And that gives me a value as 122 billion net present value of all the costs. Now the benefits are a little bit easier. We can just take the 9 billion divided by 0.06, which is P is equal to A over I, which is 150 billion per year. So now I have both the benefits and the costs, and I can take the ratio of the two, and it's 1.23, which is greater than 1, which is the evaluation criteria. So it's a good project. We would say go ahead and go with it. Now, I hope that helps you understand the solutions to the exam problem number 2. If you need to retake any of the problems, this will help you understand what you did wrong.